All right, 7 o'clock. Let's get going. One last call. If you haven't changed your name, please make it school name and then your first name. And if you have any questions tonight as we go through stuff, if you have any questions, please throw them in the chat box. And Mr. Matt will make sure that we hear about those. It's hard to believe that it's almost here, right? Some of y'all will be taking the exam this Friday. Some of y'all will be taking it a little bit later in the month, just depending. But we have been doing this together now for 9 weeks. 9 weeks. It's kind of bittersweet. I'll be glad to get my Tuesday nights back, but I also am a little sad that I won't see your faces anymore. So tonight's hat is kind of my pith helmet looking hat, because in all honesty, it's I kind of ran out of hats, and we're exploring the great big world of electrochemistry, entropy, and Gibbs free energy. So this is the second half of thermodynamics. And then how does that all relate to everything we've learned so far and then electrochemistry? And for those of you who are Star Wars fans, may the 4th be with you, please. So I actually had some downtime today and got to watch episode 4 of New Hope. So that was good for me today. Kayla, you asked about the takeaways. So if you log on to the Pear Deck, then at the end of tonight, you should get something sent to your Google Drive, whichever Google account that you sign in to Pear Deck with. And it should go to files in your Google Drive. Just look for shared with me. If anybody does not get the takeaways and you really need the takeaways, have your teacher talk to Mr. Dean, or Mr. Dean will put directions in the chat box of what to do. He can get hold of those takeaways. Some schools' spam filters are blocking my ability to be able to send you those takeaways. So with that said, let's go ahead and get cranking. Basically 3 things. Electrochemistry, which is a fancy way of doing redox reactions, but harnessing them to make electricity, like your cell phone. And then delta G and delta S. And that has to do with how do we know whether reactions will occur or not. So all right, so entropy is just a measure of disorder or randomness, right? And we know that nature tends to go towards chaos, or in other words, towards a lot of disorder. So everything that happens in the universe is creating more disorder. Now, disorder can be things like particles becoming more spread apart, like a solid to a gas. Disorder can be things like a solid dissolving and becoming ions. But it can also be about energy. So if you take molecules at one temperature and you heat them up, then those molecules, remember the Maxwell-Boltzmann distribution, the curve that kind of came up and went down? If you heat them up, they spread out. So you can have particles that are hotter have more disorder because they have more possible micro states that they can be, right? So more different speeds that they can be, kind of a thing. So whenever we say increase in entropy, that means more disorder. And whenever we say decrease in entropy, that means less disorder or more order. And that can be kind of tricky. So make sure you make this part of your study regime to know what positive and negative delta S means and what positive and negative delta H and delta G means, right? So we can predict the sign of entropy oftentimes on the AP exam. So if gases form and you started out with a solid or a liquid, gases have way more entropy because gases can exist in the whole room, right? So if you had a solid that turned into a gas in your room, then instead of being in one tiny little spot, those gas molecules can live anywhere in your room. And so we say gases have a lot more disorder or entropy. Obviously, if a solid turns into a liquid, so if ice melts, that would also be an increase in entropy because those liquid molecules can kind of spread out, right? They have what we like to use. If you go from 1 gas molecule to say 14 gas molecules, that's a great increase in the amount of disorder because you took one particle that had all those things, those atoms together in it. And in products, you turn them into a bunch of different molecules that have a total different arrangement of all the particles. So think of a piece of glass, one solid piece of glass, and when you hit it, it breaks into a bunches of pieces of glass, right? Pebbles of glass everywhere. That would be more disorder. So this is your first question. So what I want you to do is kind of circle the ones where delta S would have a negative value. So just on Pear Deck, circle the one that you think are the ones, right? It could be 1, 2, or 3, where delta S is negative. Go ahead, do that on Pear Deck. Ooh, y'all are great on the responses tonight. Great job. This is our last time together, and you guys are doing so great. All right, I'm just going to peek at a couple of the answers. Just going to peek. Okay, there's one. There's one with a lovely flower. Okay, person with the black line, I'm not real sure. You need to circle it. I'm trying to figure out which one you're talking about. Is it the first one, second one, or the third one? There's 2. Okay, great answers. All right, so just trying to look real quick at what y'all are putting. Lots of smiley faces. This is good. If you're still smiling this deep into AP chemistry, good for you. Good for you. Because I know sometimes when I taught it, I just felt like crying at this point, but that's okay. All right, so the answer here is not number 1, because number 1 is turning from a solid into a gas. So this would be delta S having a positive value, having more entropy. The second one, 2 ions becoming a solid, this is like the reverse of a KSP problem. So what you're seeing there is 2 ions that are apart from each other, right? Magnesium and the hydroxides coming together as a solid. So that would actually be a decrease in entropy. So yes, delta S would have a negative value. And in the third one, everything's a gas. But notice in the third one, you're going from 2 molecules of gas on the left-hand side to 1 molecule of gas on the right-hand side. And we would say that has more order or less disorder. So the correct answers here is Roman numeral 2 and Roman numeral 3. All right, there's 5 equations. Which one has the largest decrease in entropy? So this is an older question. They used to have 5 choices in AP exams. So which one involves the largest decrease in entropy? So remember, decrease in entropy means less disorder. Less disorder means more order. So which involves the greatest increase in order is really what the question is asking. All right, got 21 answers. Y'all are doing a great job coming in. Keep in mind that this is a real AP exam question, so you'd be expected to answer this in like a minute and a half. So part of your thinking about this is, could it be this one? Could it be that one? Sometimes you just need to get rid of 2 or 3 answers and go, well, I know it's not these. And then maybe you pick between 2, right? That's a good strategy as well. AP exam. I'm just going to peek and see what y'all think the answer is. I get a lot of E's here, a couple B's, a lot of E's. Okay, a lot of changed minds. All right, so a lot of y'all said B, and we've got 3 molecules of gas turning to 2 molecules of gas. That is a decrease in entropy. You are right. But which one involves the largest decrease in entropy? If you notice in part E, that's a solid and a gas turning into a solid. So anytime we can take a gas and turn it into a solid, that is a huge decrease in entropy. Just like if we turned a solid into a gas, like in choice A, that would be a large increase in entropy. All right, so I want you to write a response to this question. "9 weeks ago, I was drinking hot tea. Now I'm drinking iced tea." Remember, your answer should talk about the total energy and the total entropy. So what happens to the total energy and the entropy when the system reaches equilibrium? All right, I'm just going to peek at some of your answers. I'm going to start at the bottom, work my way up. The ice cube will melt. That's true. Y'all are doing a good job typing. Total energy will increase. The energy will decrease. Total energy doesn't change. Looks like y'all are giving all kinds of answers. This is great because when we make mistakes, that gives us room to be better. So whoever said it will increase then gets to a constant. You really need to be better than saying it will increase. Are you talking about the total energy or are you talking about the entropy? Like, try to be specific, especially on the AP exam, about what you're talking about. The year that they asked this question, it was actually in the form of a multiple choice question. So I just changed it up a little bit. So, all right. Help. Okay. So anytime, if you took hot water and you added a cube of ice and then you sealed it up so that there's no heat gained or lost from the surroundings, then the total amount of energy would actually stay the same. Because think about it, even though the ice would melt, the only 2 types of energy we have to deal with are potential energy and kinetic energy. And so when something melts, that involves a change from from kinetic energy to potential energy. So just make sure that as you're thinking about this, the total energy inside the system, because you're not losing or gaining any heat, the total energy would stay the same, right? Because you're not adding or taking any out. But what would happen to the entropy? Well, when the solid ice turns into liquid water, that would be more disorder. So the ice cube then becomes liquid water. That means that cube of ice is turning into a liquid, which means that would be more disorder because a solid turning into a liquid. But it's a good thinking question, right? How do you calculate delta S? Well, you've learned about this in Unit 6. You learned about how to find delta H. And this equation is on your reference sheet. But the delta S is going to be the delta S of formation of all the products minus the delta S of formation of all the reactants. So if they give you those values, you add up all the products, you subtract all the reactants, and that's how you find delta S. And by the way, this is also how you find delta G. So delta H, delta S, and delta G all run the same way. So just plug and chug, find the answer. Then there's this thing called Gibbs free energy. So the questions used to say spontaneous, and we kind of got rid of that because in your mind, spontaneous probably means it just happens, right? Well, paper burning is spontaneous. But if you just look at a piece of paper, it doesn't burst into flame. That's because thermodynamically, it is favorable that that paper will burn. The problem is, why isn't it happening? Well, the reason it isn't happening is it has a high activation energy. And that's simply it. If the conditions were exactly right, then yes, this thing would burst into flame if we could overcome that activation energy. So Gibbs free energy talks about thermodynamic favorability, which basically means once the reaction starts, can it just keep going on its own without you having to go back and do something to it? So for example, imagine a fire pit, right? You got a bunch of firewood in there. You light the fire pit. Once you get it going, that reaction continues to completion. You don't have to keep going back and feeding it some more energy to keep it going. So when we say something is thermodynamically favorable, it means that once the reaction starts, it'll just keep going. So the opposite of burning something is actually photosynthesis. So you shine a light on a leaf, the photosynthesis starts, but then if you turn the light off, it stops. So it's not that once you start it, it just goes all the time. All we need is one little bit of sunshine in a day, and photosynthesis would continue forever. Photosynthesis is a thermodynamically unfavorable reaction. We could make it happen. It's just we're going to have to add additional energy to make sure it keeps going. Right? So we're trying to use the word thermodynamically favorable instead of spontaneous. But if spontaneous is the word that you use, you'll probably still be okay. But you sound fancier when you say thermodynamically favorable. So how do we find the sign of Gibbs free energy? Well, Gibbs free energy is a function of the delta H and the T delta S. So what does nature love? Nature loves exothermic reactions. So nature loves fire. If you start a fire, it is definitely going to be thermodynamically favorable. So it likes things that are exothermic, and it also likes things that generate more disorder. Think about that firewood turning into ash and smoke particles that go everywhere, right? So it loves things that are exothermic, and it loves things that create more disorders. So things that are exothermic and create more disorder are always thermodynamically favorable. But what happens if both of those aren't true? Well, let's say it's endothermic, so it's positive delta H, and things get more orderly. Well, if things get more orderly and things are endothermic, meaning the surroundings get colder, that is never thermodynamically favorable, because those are both things that the universe and nature does not like. That's not the way they trend when they're doing things. So we can actually calculate the value for delta G using delta H minus T delta S. Now, this is on the equation sheet. However, here's something you may want to write down if you think you're going to forget it for the AP test. Delta G is typically in kilojoules per mole. Delta H is typically in kilojoules per mole, and delta S is typically in joules per mole. So when you slap numbers in the equation, you got to remember that they all have to be the same unit. So you have to change the delta S to kilojoules, or you have to change the delta H to joules. Trust me, units matter. And the temperature always, always, always has to be in Kelvin when you're doing this. Once you have the sign of delta G, then we know that things that have a negative delta G are thermodynamically favorable. So if you calculate a delta G and it says, hey, is this thermodynamically favorable? Well, if you got a negative answer, you say, yes, it was thermodynamically favorable. If it's positive, then that is something that is not thermodynamically favorable. So it can still happen. We're not saying that the reaction never happens. It just says that something is going to happen to keep it going, right? And then finally, what if delta G is 0? Well, if delta G is 0, then that means it's not thermodynamically favorable or unfavorable. It's that you're at equilibrium. So both the forward reaction and the reverse reaction are both happening at the same time. That's all what that means. You're at equilibrium. So whenever you find delta G is equal to 0, that's what that means. So I want you to write on this pear deck slide, I want you to put the sign for delta H, positive or negative, the sign for delta S, positive or negative, and the sign for delta G, positive or negative. You are doing a great job coming in with answers. All right, I got 23 answers so far. Just going to peek at your answers real quick. Positive, positive, negative. Okay. Positive, positive, positive. And a great big scribble. Positive, positive, positive. Positive, positive, positive. Positive, positive. Are you sure? Yes, I'm positive. Positive. Wow. Lots of positive. Y'all, ooh, positive, positive, negative. Negative, positive, negative. Question mark. All right. So some of these answers concern me. So let's talk about what the answer is, right? All right. So let's start with delta H. Well, the temperature decreases. So when temperature goes down, that's an endothermic reaction. So when temperature goes down, that's endothermic, and that means positive delta H. So delta H should be positive. Delta S, you're going from a solid to dissolved ions. So anytime you go from a solid and something dissolving, that's typically going to mean more disorder. And since delta S is disorder, that means that delta S would be a positive sign. Now, you don't have numbers to plug in and calculate delta G is the problem. So what is the sign? Well, simply put, you drop the solid ammonium and chloride in water and it dissolved. It happened. So did you have to do anything to it to make it dissolve? No. You added the stuff, it dissolved, boom, it happened. So what is the sign for delta G when, boom, something happens? It just happened without you having to keep it going or anything like that. We call that a negative delta G. So the sign for delta G would be negative only because you added it and boom, it happened. Look at that. There you go. Don't forget, any questions, you can throw them in the chat. If you don't have this in your notes somewhere or you have never seen this before, I would go ahead and do some kind of screen grab right now, do a screenshot or something like that. Always high, never low. Always is what I was talking about earlier. When delta H is negative and delta S is positive, nature loved both those things. It's always going to be thermodynamically favorable. The opposite of that, positive delta H and negative delta S, those are the two things nature doesn't like. And it's never going to be thermodynamically favorable, right? So what if it's a little bit of each? Well, you can either memorize this graph. When both of them are positive, it's thermodynamically at high temperatures. When both of them are negative, then it's only thermodynamically favorable at low temperatures. Now, if you're mathy, if you're a math person, then what I want you to imagine is plugging in numbers for delta H and T delta S. So let's say delta H is positive and delta S is positive. well, then delta H is positive. Nature doesn't like that. But delta S can overcome and make up for the delta H. So entropy can say, even though enthalpy, the delta H, nature is not a fan of that, delta S can be big enough to overcome the positive delta H. And that's why T delta S, if T is a really big number, meaning a high temperature, then T delta S mathematically is enough to overcome the positive delta H. So you can either think of it as memorize this chart or this graph, or you could think of it mathematically. But sometimes they'll give you a set of conditions and you need to know this always high, never low. So make sure you study this. And finally, how do we link that delta G back to equilibrium? So delta G is equal to negative RT ln of K. So sometimes it'll say, here's the K, find the value for delta G. Sometimes it'll say, here's a delta G that you calculated, find the value of K. And the trick here is you need to make sure your units match. So the R unit, R is the gas constant, but that's 8.314 joules. It's joules, which means, hey, that delta G is going to have to be in joules. And the temperature's got to be in Kelvin. And you need to know how to either take the natural log of something or the inverse natural log. Now, it's not like the whole test is going to be this sucker, but you do need to be able to use this equation. So at standard conditions, that's what that circle means, right? The little like degree symbol. At standard conditions, all the concentrations are 1. So at standard conditions, if K is equal to 1, then we go, oh, okay, you're at equilibrium, right? If delta G is negative, then that means the reaction is happening. It's thermodynamically favorable. That means K greater than 1 because it favors products. And if delta G is positive, that means, oh, not thermodynamically favorable. So it's not favorable left to right, but it is favorable right to left. Like if you flip the equation, you can flip the sign. And we know that's true. What K is less than 1 means there's more reactants than there are products. Delta G is, so let's see. So G will always be negative, only when it's thermodynamically favorable. ASFA Jesse, that delta G is 0 only at standard conditions when you're at equilibrium. So if temperature changed or something like that, then delta G wouldn't necessarily be 0. So it's kind of a special case. What I'm trying to tell you here is it used to be a lot more complicated. Like how do you find it at non-standard conditions? And there was an equation for that. But just know that this equation is just in case they give you a K value and they ask you to find delta G, or if they give you a delta G and ask you to find K. The important thing here is that the R is going to be in joules, which means your delta G is going to have to be in joules. Great questions, great questions. All right, so I'm going to get you to draw on this pear deck slide. So I want you to do part A, I, and II. So you don't have to justify your answer. All I want you to do is predict the sign of delta H and predict the sign of delta S. And then I want you to circle the graph at the bottom that shows the relationship between delta G and temperature, right? So if you increase the temperature, what would happen to delta G? Somebody asked for KP and KC. Yes, both KP and KC would work in that condition. They're not going to ask you to do KP thing because KP would require you to convert it back to KC, but you're just not going to see that on the AP exam, so don't worry about it. And y'all don't have to ask these questions privately. I mean, you can, but you don't have to. Ooh, 22 answers. This is great. I had a review session this week. Not a lot of answers coming in. Just got to be honest with you. I was a little sad. Or last week. So positive delta H and positive delta S. Positive and positive. Positive and positive. Okay. Negative and positive. All right. Some great answers. Y'all are doing better about the delta H and delta S thing. I asked this question particularly because y'all it's been a while since you did delta H, and I want you to remember something about making bonds and breaking bonds that y'all tend to mess up on. So I don't want you to do that on the AP exam. So if delta H is one sign, delta S could be that same sign, but delta S could be a different sign. So for example, Alexis, you can have something that's endothermic. So it has a positive delta H, but it causes a decrease in disorder, right? So that would be negative delta S. So you kind of have to look at the conditions for each one. They always don't go hand in hand. All right. Okay, great answer. So let's talk about how you actually do this. So the sign for delta H, the only difference between the left and right hand side of the equation is you broke a bond. Anytime you break a bond, that's endothermic. So anytime you break a bond, that is positive delta H. Anytime you form a new bond, that would be negative delta H. But since we're just breaking a bond, it would be positive delta H. You're going from one molecule on the left-hand side to two separate molecules on the right-hand side. So that would be a positive sign for delta S because you're going from one molecule to two molecules. So this takes us back to, let me run back just a little bit. Both of them are positive. When both of them are positive, delta G, then it's going to be thermodynamically favorable at high temperatures. So that means for this question, as the temperature goes up and up and up, delta G should get smaller and smaller and smaller because we want delta G to go from being positive all the way past zero until it becomes negative. Because at high temperatures, delta G is negative, meaning it's thermodynamically favorable. So you can also plug in a positive number for delta H. So plug in positive 20 and then put in delta S, make that negative 1, right? Well, delta G is going to be positive or negative depending on how big the temperature is. So let's say delta H is 20, delta S is 1, and the temperature is 10. So we get 20 minus 10 times 1, 20 minus 10 is 10. So it's a positive number. But let's take that same system and let's make the temperature now 100. Let's make the temperature really high. So then delta H still positive 20 minus 100 times 1. And so it'd be 20 minus 100. Now you get a negative number. So as the temperature goes up and up and up, mathematically you can go, oh, delta G is going to get smaller and smaller and smaller until it becomes negative. So the correct answer there is that very, very first graph, where as temperature increases on the x-axis, delta G drops, right? And this is a question from a long time ago. I haven't seen them ask one like this in a long time. Then we come to the idea of electrochemistry. So electrochemistry, basically, this used to be harder, but now that everybody's got a cell phone, you can either have a cell phone working as a cell phone, meaning the battery is powering it, or you can be charging your cell phone. So galvanic cells are a chemical energy turning to electrical energy, and electrolytic cells is the other way around, where we're taking electrical energy and changing it into like chemical energy, right? So any battery, whether you're charging it or just letting it go, is going to be a chemical reaction. And they're all redox reactions. So this kind of takes you back to Unit 4 when we were talking about redox reactions and assigning oxidation numbers. So important thing, if you don't remember how to assign oxidation numbers, I really need you to go back and do that, study that again from Unit 4 so you're ready for the AP exam, all right? The anode is where oxidation occurs. So anox, you can just remember that, right? And red cat, so reduction happens at the cathode. So these are just some vocabulary you need to know. Anox, red cat. The electricity always flows, the electrons always flow from the anode to the cathode, right? So the fat cat flow of electrons is from the anode to the cathode. The way I remember it is I just put down A because it comes first. So anode to cathode, A comes before C, right? So the electrons always flow from the anode to the cathode. So here is a cell, right? So you've got several parts. Let's see, I'm going to talk you through it and kind of just keep track of how much of this do you remember and what do you need to like kind of work on. So the electrons, according to the diagram, are flowing from the left-hand side to the right-hand side. How do I know that this is a galvanic cell and that it's not an electrolytic cell? Because an electrolytic cell would have a power source. So where it says voltmeter, it would say like power source, right? So that's my first clue. The electrons are flowing from the zinc side over to the copper. And we already said it flows from anode to cathode. So that means the zinc is the anode and the copper is the cathode. And oxidation happens at the anode, which means the zinc is going to be losing electrons and turning into zinc ions. So what's happening for a half reaction is the zinc is turning into zinc ions and electrons. The electrons flow over to the copper side. The copper ions in solution get the electrons, they absorb the electrons and turn into solid copper. So since the zinc is giving up electrons and going into solution, we expect the piece of zinc to get smaller and smaller and smaller. And that's exactly what it did. And since the copper ions in solution are being reduced and sticking to the piece of copper, we expect it to get fatter and fatter and fatter. A lot of times on the AP exam, this is exactly what they ask you to do. They say, hey, sorry, I can only do one thing at a time. Do you expect this to get bigger or smaller and why, right? So just knowing that vocabulary is going to be helpful. Now, that thing in the middle, the salt bridge, the reason why it's there is the electrons are flowing only from one side to the other side. That means one side is going to get really positive and the other side is going to get really negative because the electrons are piling up on that side. So how do you keep that charge difference, evened out? Well, the negative ions in the salt bridge travel over to the end that's getting more positive. The positive ions in the salt bridge, they travel over to the side that's getting more negative, and it kind of just evens out the charge, right? So lots of things to know here. Which way do the ions flow? Which one's the anode? Which one's the cathode? What's going to get bigger? What's going to get smaller? Those kinds of things, right? So we can also calculate the voltage of this cell, like how many volts does this thing give out? So we take the two half reactions, and these would be given to you on the AP exam. And then they say, what is it for the whole equation? Well, they can't both get electrons. Remember, redox is one thing gets oxidized, one thing gets reduced. So we need to flip one of them. We need to flip it so it's losing electrons, not gaining electrons. How do you know which one to flip? Well, for a galvanic cell, this is just a battery, the E has to be positive. So if I flip the 0.34 to negative 0.34 and added those together, not going to work. I'm not going to get a positive answer. So you want to flip the one that's more negative, and when you flip the one that's more negative, you go, aha, they're both positive. You add them together and boom, you get the 1.1 volts. So hopefully most of y'all know that. So this is a question that you might try. So some of y'all have seen this before because it's on a PowerPoint your teachers have. But let's say that this was the question. This is not something for you to answer on Pear Deck, but you'd have to determine the anode and the cathode. You'd have to calculate the standard cell potentials, so do a little bit of math. And you'd have to describe how the electrons flow. Now, the reason why I gave y'all this question is I wanted you to think about what is the question asking for so that you only answer the question listed. So determine the anode and the cathode. All you have to do is say anode is nickel or anode is zinc. You don't have to give any explanation why. It just says determine the anode and the cathode. So you're going to label one of them anode, one of them cathode. Boom, done. Calculate the standard cell potential. You're going to have to flip one of those. And this is a galvanic cell because there's no power supply here. It's just a light bulb. So you're going to have to flip one of them and do some math. But when you do that, show your calculation. You can't just plop down an answer. You have to show the calculation, even if it's adding, so that the reader knows what you're doing. And then describe how the electrons flow. Basically, you're going to say they flow from the nickel to the zinc or from the zinc to the nickel. So this is what the answer breakdown looked like. The nickel is being reduced because we have to flip the zinc. Because remember, you want to add them together and get a positive answer, right? So we want to flip the zinc and get it to be positive 0.76. And that means the zinc, instead of being reduced, is going to be oxidized, and the nickel is going to be reduced. So that means the electrons are going to flow from the thing that was oxidized, zinc, to the thing that was reduced, which means zinc is the anode, because electrons flow from the thing that was oxidized, the anode, to the thing that was reduced, the cathode. So just know your stuff, right? Let's see. Tupelo Nicole, yes, if galvanic is positive, then electrolytic has to be negative. Asking for a friend, can you flip the E values for group 1 metals? You could flip the E value for any metal. If you remember your activity series kind of a thing, you can have a cell made out of sodium and sodium ions and potassium ions. It's likely to blow up, but the activity series says which one is more likely to lose the electrons. So yes, you can flip group 1s. How do you know if it has a lower reduction potential? You just look at the numbers. That what's in that table right there is that E naught thing, that is the reduction potential, right? So the way I like to think about it is, I know when I add them together, they have to equal a positive answer. So I have to flip the 0.76 to be positive. That's the only way to get a positive answer. So I know the nickel is going to stay the way it is, and it's going to gain electrons, and that means the zinc has to flip and be losing electrons. Don't you flip the voltage that is more negative? Well, yes, that works too, Tom. I flip the negative 0.76 is more negative. Whichever method you use totally works, right? So don't learn a new method. Whatever method you use that works, that's fine. Calculate the standard cell potential. Again, it's negative 0.25. That one stays the same. and 0.76, that one stays the same. So you just add them together and you get 0.51. The important thing here is with electrochemistry, let's say you had to multiply one of those equations by something. So let's say that one thing gained 2 electrons and one thing lost 3 electrons. Even though you may multiply by some number, like you're trying to get the equation to balance, you never multiply the E naught, the voltage potential, because it's joules per coulomb. And when you multiply the equation, you're doubling the joules and you're doubling the coulombs, which is a thing of charge, right? And then finally, describe how the electrons flow. And you would say, you know, going from zinc to nickel. So sometimes they'll have you draw an arrow, right? So going from zinc to nickel. If you're not sure, the best way to miss an answer is not to answer it. So if it asks you to draw arrows on the wire indicating which way they flow, pick a direction, right? So this one would go from the right-hand side to the left-hand side, right? All right, so here's a question about, here's a cell, and this is galvanic because see how it says voltmeter, right? It tells you it's spontaneous, which means it's thermodynamically favorable, which tells you it's a negative delta G, which tells me it's like a battery. It's a galvanic cell. So we're talking about an E that's positive, a negative delta G because it's spontaneous, right? So what if I make this piece of silver super large? Oh, sorry. I was thinking y'all were answering on this one, but I guess you're not. My bad. What happens if I add the extra silver? Well, this becomes there's a thing called the Nernst equation, right? So the Nernst equation says, what if it's non-standard conditions? So you would have to write a Q expression and see where you were. You know, is Q greater than K, less than K, those kinds of things. But remember, when you add a solid has nothing to do at all with an equilibrium state. So you never worry about the solid being in there. So it doesn't matter if I made the silver electrode that big or twice as big, the voltage would not change, right? So now what would happen if I changed the concentration of the silver ion in solution? Oh, well, now I could get a change, right? If I could make the piece of cadmium even smaller, right? I could start off with it being half the size. And the solidness of it has no effect whatsoever on the voltage. They would say, what happens if I replace the salt bridge with a platinum wire? So same cell, throw a platinum wire in there. The correct answer there is the voltage is 0. It becomes 0. Why? Because you don't have a salt bridge. The salt bridge's job is to allow the ions to flow back and forth. And you're also dipping a wire in there, which gives it one more way for the electrons to flow. So the salt bridge has got to be there, or else the voltage drops to 0 and stays 0. Now, this is, I just want you to think about this for a minute. So let's say you have a AA battery, right? So imagine a AA battery, just standard battery. That is 1.5 volts. I don't know if you knew that or not, but let's just say AA battery, 1.5 volts. You plug it into a device and you let it go for a little while. Well, do you think that over time, as the battery works and current flows, that the voltage should go down or that the voltage should go up? Well, to me, a dead battery is one that has a voltage of 0. So if it starts out at 1.5 volts and you let it run for a little bit and it's going to be dead when it gets to 0 volts, well, then that means as time goes on, the voltage decreases and decreases and decreases. So as a battery runs, then that voltage decreases over time. And at some point it just you run out, and we call that a dead battery. Now, how do we tie these two things together? How do we tie together the Gibbs free energy and the electrochemistry? Well, we know that E has to be positive for a galvanic cell. So imagine plugging in a number for N. So let's say 2 for moles of electrons. And F is just a constant, right? It's just a constant. So a negative times 2 times a constant times a positive E. That means when E is positive, delta G is negative. So in electrochemistry, whenever you've got a galvanic cell, that's negative delta G and positive E naught, or a standard cell potential, right? Sometimes they'll give you an equation and say, hey, find the E naught. And then they say, find delta G. So even if you're wrong with your answer for E naught, let's say you flipped it wrong, right? You're like, oh, I forgot, oh, I messed it up. As long as you calculated delta G correctly based on your number, boom, you still get that point. The N, the number of moles, comes from the balanced equation, right? So the example I was just showing you is like, it's like 1 electron or 2 electrons being transferred according to the balanced equation. Just keep in mind here that E is volts. And on the reference sheet, it tells you that a volt is joules per coulomb, which means your answer here is going to come out in joules, which means you have to be very careful with your units here and know that E is in joules, and it's going to probably ask you to find the answer in kilojoules. So now is not the time to give up on, I just plug numbers in and never pay attention to units. So these are some differences and similarities between the two things, and this should be available on the takeaway. But galvanic cells produce electricity. Electrolytic cells, you have to provide the electricity. So using your phone, charging your phone. Typically in a galvanic cell, you have 2 containers with a salt bridge. In an electrolytic cell, you can have everything in 1 container, kind of a thing. And then there's some more differences. And what's important is that you just understand, which one to flip, which end is going to be the anode and the cathode, which one loses electrons and which one gains electrons, kind of a thing. And then just like somebody asked before, galvanic E is positive, electrolytic E is negative. When you're charging it, delta G is positive, because we know phones don't charge themselves. How much better would life be if that happened? All right, so let's look at some more things. We can also calculate electrical current. So up to now, we've talked about voltage. Voltage you can think of as the water flowing out of a hose, right? So you can either have a hose with the water flowing out. You can stick your finger over the end of it and make the water spray out a lot faster. So that's like affecting the water pressure. But you can either do that with a little tiny hose, or you can do that with a great big pipe. So the size of the pipe is like amperage, and that's the current that we're talking about. And then electrical current is basically we're measuring how much charge gets transferred over time, right? So the symbol for it is I, and this is all on your equation sheet, right? So no need to worry about it. But it's the amount of charge over time. So it's measured in amps, which is coulombs per second. So maybe you don't know what an amp is. The plug in your wall is probably like a 20 amp circuit. It's the idea of how much electricity can flow through there at one time. And if too much flows, then it could cause a fire. So that's why you have circuit breakers. Your car battery, even though it's only 12 volts, while your wall socket is 120, even though it's lower voltage, it can crank out 100 amps. So it can produce a much greater amount of electricity, which is why the wires on your car battery tend to be pretty thick, because they have to be able to deliver a lot of current, even though it's a lower voltage. So we can work a problem like this, right? So we can say, I want to have an electrolytic cell that does 11.5 grams of metal. Well, we know anytime you're given grams, when in doubt, mole that sucker out. So the idea is we change from grams of silver to moles. And then I know that silver ion has a +1 charge. So that it means it needs 1 mole of electrons for every 1 mole of silver because it has a +1 charge. And then we use Faraday's constant, 96,485 coulombs per mole of electrons, also on the sheet. And that gives you a total number of coulombs. And then the amperage, 2.5 amps, is number of coulombs per second. So 2.5 amps, you know the number of coulombs, you can solve for the number of seconds. All right, so consider the reaction below, which is spontaneous. Can you tell me whether the standard entropy change is positive, negative, or 0 and justify your answer? So take a stab on Pear Deck of answering what you think this is. Okay, I got 21 answers so far. Let me see what we're getting to. Delta S is negative. Okay, so avoid comments like it would be more negative because it's going from more chaos to more order. You're using the words order and chaos to define more order. So that doesn't really explain why. You need to point to something in the chemical equation that tells you it's more order. So just be very careful with your answers. I'm a little lost. That's totally okay. Just taking a guess. That's fine. All right, so in this question, I'm going to show you a bunch of them, and then we're going to touch on the answers. So this is all part of one great big question. So first of all, is delta S positive, negative, or 0? Justify your answer, right? The second part is which factor, the delta H part or the delta S part, is the major driving force for the reaction. What is making this spontaneous, right? So a number of y'all pointed out you're going from a gas to a solid in the equation. And if you're going from a gas to a solid, that's going to be a decrease in disorder or a decrease in entropy. So the sign of delta S here would be negative. So is delta H the thing that's making it spontaneous, or is delta S the thing that's making it spontaneous? What would your answer be? I'm not sure. That's a fine answer. All right, so we're going to we'll come back to what the answers are here in a minute, right? So then the question says, how is the value of standard free energy, delta G, affected by an increase in temperature? So the reason why I wanted y'all to see this was you may have said positive delta S in the first part. And if you said positive delta S in the first part, that could affect your answer for part I. If you said negative for part I, then that's going to affect your answer for I. So my point is, when they ask a question like, how is delta G affected? There is no one answer to that. It kind of depends on your previous answer. And then the question goes on to say, some reactions that are predicted by their sign of delta G to be thermodynamically favorable do not proceed at a measurable rate. So even though it is supposed to happen, it doesn't happen. And you would have to account for this contradiction. So how would you account for this contradiction? What can you like, oh yeah, that makes sense because, and then the question asks, a suitable catalyst increases the rate of such a reaction. What effect does the catalyst have on delta G for this reaction? So my point being, sometimes you guys get questions and you're like, I don't even know. Like, how am I supposed to know these things? Well, maybe you don't know I, but maybe you know part B, right? Or maybe you don't know part B, but you know part A, right? So always read the entire question and do all the parts that you can. And remember, the best way to miss a question is not to answer the question at all. So if we look at what the answers are, so for part I, it's going to be negative because a gas is becoming a solid. Now, how does nature feel about a negative delta S, about more order? Nature doesn't like it. So if nature doesn't like the entropy part, then what's the driving force? The negative delta H that's given to you in the equation. So since delta H is negative, that's the universe going, yes, love it. That's what's going to make me thermodynamically favorable or spontaneous. How is the value of the standard free energy affected by an increase in temperature? Well, this is where you know that always high, never low kind of a thing, graph, because delta H is negative, it's winning. But if the temperature gets high enough, that negative delta S, it could start to be a problem. So as the temperature gets higher and higher and higher, delta G is going to float ever closer to becoming positive. So how is the value affected by an increase in temperature? As the temperature increases, that delta G could get larger and larger and larger, becoming more and more towards the positive side. Now, even though it's supposed to happen, spontaneous, but it doesn't, what is that? That's a kinetics question. Things that are supposed to happen that don't, that's usually because of high activation energy. And what does a catalyst do? Well, a catalyst doesn't affect the value for delta G. Notice, nowhere in this equation is there a spot for a catalyst. All that the catalyst does is provide a lower activation energy. So what is the effect of a catalyst on delta G? None at all, none whatsoever. Right, so go ahead and take a stab at writing or coming up with the, identify the chemical that is produced at the cathode, right? So which one of those things is going to be produced at the cathode? And I know I'm running a little bit over and I are trying to do that. Let's see, some questions that y'all have as y'all are answering. What is the definition of delta H? That is the heat either released during an exothermic reaction or absorbed during an endothermic reaction. Like hotter things is a negative delta H and colder things a positive delta H. So delta H and delta S, there is no correlation to them. You can have positive both, you can have negative both. You can have one positive and one negative. Delta H has to do with whether or not it releases energy or not, and delta S has only to do with is there more order or not. You can't say, oh, where one is, the other one automatically is. Now, here's the thing that I want you to notice about this question I just gave you, and we'll finish up here in a minute. It says you pass a direct current. So this direct current says, ooh, this is a power supply. Since I've got a power supply in here, that means I want a negative E naught. So I want a negative potential, negative number of volts, right? So knowing that when you add them together, you want the answer to end up negative, then what we would do is we would flip that second one. And when we flip the second one, that would tell us, that would give us overall a negative answer. So here is, no, not this one, hang on. Yeah, this one, sorry. Okay, so let's say that you found that it told you the E naught for the cell is 0.62, positive 0.62, right? So if you got it to be positive 6.2, then really what you're saying is one of them is 0.34, what's the other one? So if you notice in the equation, you've got solid copper on the left-hand side of the big equation up top, and you've got copper ion on the right-hand side. That's your clue about which equation you have to flip. Because in the table down below, it's copper ion turning into copper solid. So the clue that you have to flip the copper equation comes from the equation up top. So that first equation with the copper ion plus 2 electrons becomes copper solid. You flip that one, and when you flip it, you flip the sign, and that's how you arrive at the value of 0.96. But the next thing would ask you, okay, how do I calculate delta G? Well, delta G is negative N FE. So all I want for you to think about, because I got to finish up, is what is N? If it's negative N FE, and for part A, you found an E, you found a voltage to be 0.62, right? It's up top. So if you knew that E was 0.62, then what is N that you're going to plug into this sucker? And you can just write that right in your response. And I'm just going to peek real quick. I got 6, 6, 6, 6. Right, very good. Okay. So the key here is the copper equation takes 2 electrons. The NO3 equation takes 3 electrons. So to get it to balance, you got to go, what number do 2 and 3 have in common? And 2 and 3, the least common multiple would be 6. So you would plug in N of 6, and you would solve for the value of delta G. And they gave you 1 point that year for just knowing 6, just knowing 6. And they gave you 1 point for the correct answer. Now, where most people lost the point is they just found out the answer negative 360,000. Like, they didn't even pay attention to units. So you got to remember that a volt is a joule per coulomb. And so you had to change the joules to kilojoules. So now you found the E in part A, you found the delta G in part B. In part C, predict whether the delta S is greater than, less than, or equal to 0. So the trick here is greater than 0 is positive, less than 0 is negative, or equal to 0. So just for part C, go ahead and predict your the sign of delta S. Delta S is 0. Okay, so a lot of y'all are saying positive, and I will say you are right. It's positive. However, notice what the question asks you for. Predict whether it's greater than 0, less than 0, or equal to 0. You should not be writing positive or negative. You need to answer what they asked you to answer. So if it's positive, then write greater than 0. If it's negative, write less than 0. But try not to use the word positive when the question actually asks you greater than, less than, or equal to 0. And then justify your thing comes from the fact that there's a solid on the left and you got a gas coming out on the right, right? So that's a really big deal. And finally, our last one I wanted to show you is sometimes the questions are easy like this. So what does a really big K value mean to you? If it's not just a little big, it's 3.7 times 10 to the 15th. So when K is exceedingly large, what does that tell you about the E and the sign of delta G? And oftentimes you see this kind of question on the AP exam. This is the one we're going to end with. Tom, you asked if you would not get a point if you just said positive. I was not there when they scored that, but probably not, because you had to say greater than 0, less than 0, or equal to 0. So when they tell you what to write and you don't write it, that's on you, man. So I'm just going to, oh, we've only got 19 answers so far. So keep going. So a lot of y'all are saying A, a couple C's, and an E. So if K is really big, that means the reaction really happens, right? If K is really large, that means reactants are turning to products. So what do you know about a reaction that definitely happens? Boom, delta G is negative. So if delta G is negative, it can't be B, it can't be C, and it can't be E. That leaves you with A and D. And if it's K is really big and the thing is just happening, then that's thermodynamically favorable. That's a galvanic cell. And so for a galvanic cell, E is positive and delta G is negative. So boom, answer is A. Thank you guys so much for coming. Those of you taking the exam this Friday, best of luck, best of luck, best of luck. And those of you who are waiting until later, use this time for studying. Use this time for studying. Thank you so much for coming tonight. If you guys have any questions, I'll be happy to answer them. Just throw those in and I will be happy to answer them.